let yourself settle into a comfortable position. Feel the weight of your body being supported, whether you're lying down, sitting, or nestled into your favorite spot. Notice how your breathing happens naturally, without any effort from you, each breath flowing in and out like gentle waves on a shore. Tonight, we're going to explore one of the most profound questions humans have ever asked. But don't worry about keeping track of every detail. Just let the words wash over you, like listening to a story told beside a warm fireplace on a cold evening. We're going to think about the universe, about space itself, and about a question that sounds simple, but opens doorways into the deepest mysteries of existence. The question is this: if the universe is expanding, what is it expanding into? You've probably heard that the universe began with the Big Bang 13.8 billion years ago, and that it's been growing ever since. But if the universe is everything that exists, then what lies beyond it? What could possibly be outside to expand into? This question has puzzled philosophers for thousands of years and scientists for decades. The answer, as you'll discover, challenges our most basic intuitions about space, time, and existence itself. So breathe deeply, relax completely, and let's drift together through the cosmos, exploring a paradox that reveals the strange and beautiful nature of reality. But before we begin our journey, if you're enjoying this content and would like to see more explorations of cosmic mysteries designed to help you relax and drift into peaceful sleep, please consider subscribing to The Science Pillow and leaving a like on this video. Your support helps us continue creating these calming journeys through science and the cosmos. Now, let's return to our question and begin unraveling this magnificent puzzle: the nature of expansion. What we observe. The discovery that the universe is expanding stands as one of the most revolutionary insights in human history. To understand what expansion means and why it creates such a fascinating paradox, we need to journey back to the early 20th century, to a time when astronomers believed the cosmos was static and unchanging. Picture the night sky as people saw it 100 years ago. The stars seemed fixed in their eternal patterns, the constellations unchanging across generations. Most astronomers believed that the universe, while vast, was essentially motionless on the largest scales. Yes, planets orbited stars and stars moved through space, but the overall structure of the cosmos was thought to be permanent and stable. Even Albert Einstein, when he applied his newly developed theory of general relativity to the entire universe in 1917, was so convinced that the cosmos must be static that he added a mathematical term called the cosmological constant to his equations, specifically to prevent the universe from expanding or contracting. Then came Edwin Hubble. Working at the Mount Wilson Observatory in California in the 1920s, Hubble was studying distant galaxies, or what were then called spiral nebulae. Using the observatory's powerful telescope, he measured something unexpected. When he analyzed the light from these distant galaxies, he noticed that it was shifted toward the red end of the spectrum compared to what he would expect. This red shift, as it's called, is similar to how the pitch of an ambulance siren drops as it speeds away from you. When a source of sound moves away, the sound waves get stretched out, lowering the pitch. Similarly, when a source of light moves away, the light waves get stretched to longer wavelengths, which for visible light means shifting toward the red end of the spectrum. Hubble found that almost every galaxy he observed showed this redshift, indicating they were all moving away from us. But the truly revolutionary discovery came when he measured how much redshift different galaxies showed and compared it to their distances. He found a clear relationship. The farther away a galaxy was, the faster it appeared to be receding. A galaxy twice as far away was moving away twice as fast. This relationship, now called Hubble's law, could mean only one thing. The universe itself is expanding. Imagine a loaf of raisin bread rising in the oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any particular raisin, all the other raisins appear to be moving away, with the more distant ones receding faster. Importantly, no raisin is at the center of the expansion. There's no special location from which everything is fleeing. Every point in the bread sees the same pattern. This is precisely what Hubble discovered about our universe. From our vantage point in the Milky Way, we see all distant galaxies receding from us. But an observer in any of those distant galaxies would see exactly the same thing. All other galaxies receding from them. But what does it mean to say the universe is expanding? This is where our intuitions start to lead us astray. When we think of something expanding, we naturally picture it growing into the space around it. A balloon inflates by pushing outward into the air around it. A city expands by spreading into the surrounding countryside. But the universe isn't expanding into anything outside itself, because there is no outside. The universe, by definition, is everything that exists. Space itself is what's expanding. Let me try to make this clearer. When we say the universe is expanding, we don't mean that galaxies are flying through space, racing outward from some cosmic center like shrapnel from an explosion. Instead, space itself is stretching and growing. The galaxies are relatively stationary within space, but the space between them is increasing. Think of it this way. Draw two dots on a deflated balloon, then inflate it. The dots move apart, but they haven't traveled across the rubber surface. Instead, the rubber itself has stretched, carrying the dots along with it. Modern measurements have refined Hubble's discovery with extraordinary precision. The current expansion rate, known as the Hubble constant, is measured to be about 73 kilometers per second per megaparsec. What does that mean? A megaparsec is about 3.26 million light years, a convenient unit for measuring cosmic distances. The Hubble constant tells us that for every megaparsec of distance between us and a galaxy, that galaxy is receding an additional 73 kilometers per second faster. A galaxy 1 megaparsec away recedes at 73 kilometers per second. A galaxy 2 megaparsecs away recedes at 146 kilometers per second. A galaxy far enough away recedes faster than the speed of light. But this doesn't violate relativity because the galaxy isn't actually moving through space at that speed. The space between us and it is expanding at that rate. Observations over the past few decades have revealed something even more remarkable. Not only is the universe expanding, but the expansion is accelerating. Distant galaxies are receding faster and faster as time goes on. This acceleration was discovered in 1998 by two independent teams studying distant supernovae, and the discovery was so important that it earned a Nobel Prize in Physics in 2011. The acceleration implies that some kind of energy, which physicists call dark energy, permeates all of space and pushes it to expand faster and faster. Today, we can observe this expansion directly. Astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. Detailed measurements by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory have mapped tiny temperature variations in this radiation across the entire sky. These patterns tell us about the conditions in the early universe and confirm that space has been expanding for nearly 14 billion years. The expansion we observe isn't happening within our galaxy, or even within our local group of galaxies. Gravity binds these structures together strongly enough that the expansion of space doesn't pull them apart. The Milky Way and the Andromeda Galaxy are actually falling toward each other despite the universe's expansion, because their mutual gravitational attraction overcomes the cosmic expansion at these relatively small scales. It's only when we look at very large scales, at the distances between galaxy clusters and superclusters, that the expansion becomes dominant and we see everything moving apart. So we observe with certainty that the universe is expanding. Space itself grows larger with time. Distant galaxies recede from us, and the farther they are, the faster they recede. This expansion has been happening for nearly 14 billion years, since the universe began in an incredibly hot, dense state we call the Big Bang. But this brings us back to our central question. If space itself is expanding, what is it expanding into? Understanding space itself. To grapple with the question of what the universe expands into, we need to fundamentally rethink what we mean by space. This requires us to let go of some deeply ingrained intuitions about the nature of reality, intuitions that served our ancestors well when dealing with objects on human scales, but that break down when we contemplate the cosmos as a whole. We naturally think of space as a container, an empty three-dimensional box in which things exist and events unfold. In this view, space is like a stage on which the cosmic drama plays out, separate from and independent of the objects within it. This perspective made sense for thousands of years and worked well for everyday purposes, but in the early 20th century, Einstein's theories of relativity revealed that this intuitive picture is fundamentally wrong. According to general relativity, space and time are not separate, independent entities. They're woven together into a single four-dimensional fabric called space-time. More importantly, this fabric isn't static and unchanging, it's dynamic and flexible, warping and bending in response to the presence of matter and energy. Massive objects like stars and planets don't just sit in space, they curve the space-time around them. This curvature is what we perceive as gravity. Imagine a heavy ball placed on a stretched rubber sheet. The ball creates a depression in the sheet, curving it downward. Now imagine rolling a smaller ball near the large one. The small ball will spiral inward toward the heavy ball, not because some force is pulling it, but because it's following the curved surface of the sheet. This is analogous to how gravity works in general relativity. Earth orbits the sun not because an invisible force pulls on it, but because the sun's mass curves space-time, and Earth follows the natural paths, called geodesics, through that curved space-time. But here's what's crucial for understanding cosmic expansion. Space-time itself can expand or contract. It's not a fixed background, but something that can grow, shrink, stretch, and warp. When we say the universe is expanding, we mean that the metric of space-time, the way distances are measured, is changing. Rulers are getting longer, or, equivalently, the space between distant objects is increasing even if those objects aren't moving. Think about what it means to measure distance. If you want to know how far apart two cities are, you might use a ruler, or, more practically, measure the time it takes light to travel between them. But what if the ruler itself were stretching? What if the space through which the light travels were expanding as the light makes its journey? This is precisely what happens in our universe. Light from a distant galaxy travels through space for billions of years, but during that journey, the space itself expands, stretching the light waves to longer wavelengths. The expansion of space is intrinsic. This word is important. Intrinsic means the expansion is a property of the space itself, not something happening within a larger container. It's like the surface of a balloon inflating. If you were a two-dimensional creature living on the balloon's surface, you would observe that distances between all points on the surface were increasing. But the balloon isn't expanding into your two-dimensional world, it's expanding in a third dimension that you, as a two-dimensional being, cannot perceive. Similarly, our three-dimensional space expands, but not into some higher dimensional void. The expansion is simply what the space does. People often use the balloon analogy to explain cosmic expansion, and it's helpful, but we need to be careful with it. Picture the surface of a balloon, not the interior, just the two-dimensional rubber surface. Draw galaxies on this surface with a marker. Now inflate the balloon. As it expands, all the galaxies move apart from each other. No galaxy is at the center of the expansion. Because the center isn't on the two-dimensional surface, it's in the three-dimensional space around the balloon. From any galaxy's perspective, all other galaxies appear to be moving away. This analogy helps us understand several important points. First, the expansion doesn't have a center within the observable space. Second, the expansion is uniform, meaning every region of space expands at the same rate. Third, and most relevant to our question, the surface of the balloon doesn't expand into the two-dimensional surface itself. It expands in the third dimension. But here's where the analogy breaks down. Our three-dimensional universe isn't necessarily expanding into a fourth spatial dimension. It might just be expanding intrinsically, with no need for a higher dimensional space to expand into. This is profoundly difficult for our minds to grasp, because all of our experience involves things expanding into surrounding space. A plant grows by extending into the air around it. A city expands by building outward into previously undeveloped land. Water expands when it freezes, pushing outward against its container. We have no everyday experience of space itself expanding without expanding into something. But the mathematics of general relativity tells us that this is not only possible, but is exactly what's happening to our universe. Space-time can curve back on itself, creating geometries that have no edge or boundary, but are nonetheless finite. A two-dimensional analogy would be the surface of Earth. You can travel in any direction on Earth's surface and never reach an edge or boundary. You can circumnavigate the globe and return to your starting point. The surface is finite in area, but has no edge. Similarly, our three-dimensional universe could be finite in volume, but unbounded, with no edge or outside. Alternatively, the universe might be infinite in extent. In this case, the expansion means that the density of matter and energy decreases over time as the same amount of stuff gets spread over an ever larger infinite space. This seems to create a different kind of paradox. How can something infinite get bigger? But mathematically, it makes perfect sense. Imagine the set of all integers, negative infinity to positive infinity. Now imagine doubling the spacing between each integer. The set is still infinite, but the distance between any two specific integers has increased. The infinite universe expands in a similar way. The key insight is that space isn't a thing that exists. It's a relationship between things that exist. When we talk about the distance between two galaxies, we're describing a relationship between those galaxies. When space expands, we're saying that this relationship is changing over time. The galaxies themselves might not be moving through space, but the relationship, the distance between them, increases. Think about a coordinate grid, the kind you used in mathematics class with x and y axes. You can describe the position of any point using coordinates, but the grid itself isn't a physical thing. It's just a system for describing relationships between points. In general relativity, space-time is similar. It's a mathematical framework for describing how events relate to each other in space and time. The expansion of the universe means this framework is dynamic, not static. Another way to think about it, space is what we measure with rulers and clocks. It's the thing that allows us to say two events are separated by a certain distance or a certain time interval. When space expands, the measurements change even if nothing has moved in the conventional sense. A galaxy a billion light years away today will be farther away tomorrow, not because it traveled anywhere, but because the space between us and it grew. This brings us closer to answering our central question. If space is not a container, but rather a description of relationships, then it doesn't need to expand into anything. The expansion is simply a change in those relationships over time. There is no outside, because outside is a spatial concept. It refers to a region of space beyond some boundary. But space itself doesn't have a boundary within space, because any such boundary would itself be part of space. Imagine you're a character in a video game, living in a purely digital world. Your world consists entirely of the pixels on the screen and the code that governs them. From within the game, you can move around, interact with objects, and explore. But it makes no sense to ask what's outside the game world, because outside is not a concept that exists within the game. The game world is all there is for you. Similarly, for us as inhabitants of the universe is all there is. Asking what's outside it is like asking what's north of the North Pole. The question assumes a framework, a spatial relationship that doesn't apply. But doesn't space have to end somewhere? Our intuition screams yes. Surely if you traveled far enough in a straight line, you'd eventually reach a boundary, a cosmic wall or edge, where space simply stops. But this intuition comes from our experience with objects in space, not with space itself. Every object we encounter has boundaries. Every room has walls. Every journey has a starting point and a destination. But space as a whole doesn't have to follow these rules. In a flat, infinite universe, you could travel in a straight line forever and never reach an edge, because there is no edge. The universe simply goes on infinitely in all directions. In a closed, finite universe, you could also travel in a straight line forever without reaching an edge, but eventually you'd return to your starting point, just as you would if you traveled in a straight line along Earth's surface. Either way, there's no boundary, no edge, and thus no outside to expand into. The expansion of space, then, is not expansion into anything. It's simply the evolution of the cosmic fabric over time. Distances increase. The universe becomes less dense. Light from distant sources gets stretched to longer wavelengths. All of this happens not because space is pushing into some external void, but because the intrinsic geometry of space itself is changing. Into what paradox? Now that we've established that space can expand intrinsically without expanding into anything, let's confront head-on why this seems so impossible to our intuitions, and why the question, what is the universe expanding into, persists as one of the most commonly asked questions about cosmology. The paradox arises from a deep-seated assumption about how reality works. We assume that for something to grow, there must be room for it to grow into. This assumption is so fundamental to our experience that violating it seems absurd. When a balloon inflates, it displaces the air around it. When a city expands, it spreads into the countryside. When the water level in a bathtub rises, the water moves into space previously occupied by air. In every case we've ever encountered, expansion requires pre-existing space to expand into. But the universe is not like these examples, because the universe is not an object in space. It is space. The universe doesn't exist within a larger volume. It is the totality of all volume. There's nothing outside it, for the simple reason that outside is a spatial concept that only makes sense within the universe itself. Let me try yet another approach to make this clearer. Think about time. Time, as far as we can tell, doesn't exist inside anything. We don't imagine that time flows through some larger temporal container. Time simply is. Now ask yourself, what does time expand into as it moves forward? The question doesn't make sense because time isn't expanding into anything, it's just progressing. Similarly, space isn't expanding into anything, it's just evolving. But there's a subtlety here that we need to address. When physicists say the universe isn't expanding into anything, they're talking about the universe as a whole, the totality of all that exists. However, we need to be careful about the distinction between the observable universe and the whole universe, because this distinction creates further confusion. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's a sphere centered on Earth, extending about 46.5 billion light-years in every direction. You might wonder why this radius is larger than the age of the universe in years, 13.8 billion. The reason is that space has been expanding while the light traveled. So objects that emitted light 13.8 billion years ago have since moved much farther away. The observable universe is vast, containing hundreds of billions of galaxies, but it's almost certainly just a tiny fraction of the whole universe. The whole universe might be vastly larger than the observable portion, perhaps even infinite. When we say the universe is expanding, we mean the whole universe, not just the part we can see. The edge of the observable universe is not a physical boundary, it's simply a horizon beyond which we cannot currently see. Light from regions beyond this horizon hasn't had time to reach us yet, but those regions exist nonetheless, and they're expanding just like the regions we can observe. This distinction sometimes leads people to ask, if there are regions of the universe beyond what we can observe, couldn't the universe be expanding into those regions? But no, this misunderstands the situation. Those distant regions are part of the universe. They're regions of space, not something else that space is expanding into. The universe includes all of space, both the parts we can see and the parts we cannot. Here's another common source of confusion. In the balloon analogy we used earlier, the balloon's surface expands into the three-dimensional space surrounding it. People naturally ask, doesn't our three-dimensional universe similarly expand into a fourth spatial dimension? This is a good question, and the answer is maybe, but it doesn't have to. In some theoretical frameworks, our universe is embedded in a higher dimensional space. String theory, for example, proposes that reality has 10 or 11 dimensions, most of which are curled up so small we can't perceive them. In some versions of these theories, our observable universe might be a three-dimensional brain, short for membrane, floating in this higher dimensional space like a sheet of paper floating in a room. If this is correct, then in a sense our universe does expand into a higher dimensional space. But standard cosmology based on general relativity doesn't require this. Our universe can expand intrinsically without needing a higher dimension to expand into. The mathematics works perfectly well either way. Just as the integers can be spaced farther apart without needing to exist in some meta-mathematical space, our three-dimensional space can expand without needing a fourth dimension to expand into. The possibility that our universe is embedded in a higher dimensional space raises other interesting questions. If there are extra dimensions, could there be other three-dimensional universes out there? Other brains floating in the higher dimensional space? Could our universe collide with another universe? These are active areas of theoretical research, but they remain speculative. The point is that even if our universe does exist in some higher dimensional space, that still doesn't change the fundamental answer to our question. The universe, defined as everything accessible to us, everything causally connected to us, all the space we could ever observe or interact with, doesn't expand into anything we could meaningfully call outside. Let's address another aspect of the paradox. People sometimes ask, if the Big Bang happened at a single point and the universe has been expanding ever since, shouldn't we be able to identify the center of that expansion? Shouldn't there be a point in space from which everything is fleeing? The answer is no, and the question rests on a misconception. The Big Bang didn't happen at a point in space. It happened everywhere. Imagine rewinding the expansion of the universe like a movie in reverse. Galaxies get closer together. The universe becomes denser and hotter. Eventually, all the matter and energy we can observe today gets compressed into a very small volume. But here's the key. That small volume was all there was. It wasn't a small region within a larger space. It was the entirety of space at that time. If the universe is infinite now, it was infinite then too, just much denser. If the universe is finite but unbounded, like the surface of a sphere, then in the past it was a smaller sphere, but still with no center on the surface itself. Either way, the Big Bang happened everywhere. At once, there's no special location in space that was the site of the Big Bang. Every point in space has an equal claim to being where it all started. This leads to a profound realization. When we look out into space, we're also looking back in time because light takes time to travel. The farther away we look, the farther back in time we see. The most distant objects we can observe are seen as they appeared when the universe was very young, less than 1 billion years after the Big Bang. The cosmic microwave background radiation, the faint glow we detect from all directions, was emitted about 380,000 years after the Big Bang, when the universe first became transparent to light. But this light didn't come from a distant location in space. It came from the space where we are now. In the distant past, this very location was part of the hot, dense, early universe. The microwave background radiation we detect today was emitted from our location when the universe was young. It has been traveling through expanding space ever since, and because of that expansion, it now appears to be coming from a vast distance away. This might seem contradictory, but it makes sense. Once you remember that space itself has expanded, the photons in the cosmic microwave background were emitted from matter that was close to where we are now, but that matter has since moved far away due to the expansion of space. The light has been traveling for nearly 14 billion years, but during that time, space has stretched enormously, so the matter that emitted the light is now about 46 billion light years away. All of this brings us back to the central insight. The expansion of the universe is not expansion into a pre-existing void. It's not galaxies flying apart through static space. It's space itself growing, stretching, evolving. And space doesn't need somewhere to expand into, because space is not a thing that exists in some larger context. Space is the context. It's the framework within which existence happens. The question, what is the universe expanding into, persists because it's grammatically well-formed and seems to make sense. We can say the words and they sound like they ought to have an answer. But some questions, even when they can be clearly stated, rest on false assumptions. This question assumes that expansion must be expansion into something, that space must exist within a larger space. But this assumption, natural as it seems, is wrong. The universe expands without expanding into anything, because there is no outside for it to expand into. The universe is all there is. The observable universe versus the whole universe. To deepen our understanding of cosmic expansion and the nature of space, we need to carefully examine the distinction between the observable universe and the whole universe. This distinction is crucial because much of the confusion about what the universe expands into stems from conflating these two very different concepts. The observable universe is, in a sense, a personal bubble. It's defined by what you, or any observer, can potentially see. Light travels at a finite speed, about 300,000 kilometers per second, and the universe has existed for a finite time, about 13.8 billion years. This means there's a limit to how far we can see. Light from objects farther away than this limit hasn't had time to reach us yet. But there's a complication. The universe has been expanding while light traveled toward us, so objects that emitted light near the beginning of time have since moved much farther away. When we account for this expansion, the radius of the observable universe turns out to be about 46.5 billion light years. This is the distance to the cosmic horizon, the boundary of the region from which light could have reached us. Think of this boundary as an observer-dependent horizon, similar to how there's a horizon when you stand on a ship in the ocean. You can only see to a certain distance because of the curvature of Earth's surface. Objects beyond the horizon exist, but you can't see them from where you are. Similarly, galaxies beyond our cosmic horizon exist, but we can't observe them because their light hasn't reached us yet. The observable universe contains an estimated 200 billion to 2 trillion galaxies, each containing billions to hundreds of billions of stars. The sheer number of objects within our observable bubble is staggering, almost incomprehensible, and yet this might be just a tiny fraction of the whole universe. In fact, most cosmological models suggest that the observable universe is like a grain of sand on an infinite beach compared to the totality of what exists. The whole universe, meaning everything that exists anywhere, is likely vastly larger than what we can observe. It might even be infinite. Observations of the cosmic microwave background radiation and the large-scale structure of galaxies have allowed cosmologists to measure the curvature of space with remarkable precision. The results indicate that space is very close to being perfectly flat. In the context of cosmology, flat doesn't mean two-dimensional. It means that the geometry of space obeys Euclidean rules on large scales. Parallel lines remain parallel, the angles of a triangle add up to 180 degrees, and so on. Why does this matter for the size of the universe? Because the geometry of space is related to whether the universe is finite or infinite. If space has positive curvature, curving back on itself like the surface of a sphere, then the universe is finite in volume even though it has no boundary or edge. If space is perfectly flat or has negative curvature, then it's likely infinite in extent, stretching on forever in all directions. The measurements we have suggest that if space does have any curvature, it's so slight that we can't detect it. This points toward a flat or nearly flat universe, which in turn suggests that the universe is probably infinite. But we can't be completely certain. It's possible that space does curve back on itself on scales much larger than the observable universe, making the whole universe finite but so large that we can't detect the curvature. If the universe is infinite, this creates fascinating implications. An infinite universe means there's no center and no edge. Every point is essentially equivalent to every other point. The laws of physics are the same everywhere, and the distribution of matter and energy, while varying locally, is statistically the same across the whole universe. This principle is called the cosmological principle. The universe is homogeneous and isotropic on large enough scales. An infinite universe also means there's an infinite amount of matter and energy. Not just a very large amount, but truly infinite. This seems mind-boggling, but it's a logical consequence of infinite space with a roughly uniform density. Moreover, in an infinite universe, every possible configuration of matter that doesn't violate the laws of physics will occur infinitely many times. There would be infinitely many galaxies like the Milky Way, infinitely many planets like Earth, and statistically speaking, infinitely many identical copies of you, living lives identical to yours. This prediction troubles some people philosophically, but it follows directly from the mathematics of an infinite, homogeneous universe. Now, whether the universe is infinite or just vastly larger than the observable portion, the expansion we observe affects the whole universe uniformly. Space expands everywhere at the same rate, described by the Hubble constant. This means that regions of space beyond our current horizon are also expanding. Galaxies we cannot yet see are receding from each other, just like the galaxies we can observe. But here's something remarkable. Because the expansion is accelerating, driven by dark energy, there are regions of space that we will never be able to observe, no matter how long we wait. These regions are already receding from us faster than light, and the expansion rate is increasing. This means that the light they're currently emitting will never reach us. The cosmic horizon represents not just what we can see now, but what we will ever be able to see. This raises a poignant point. There are galaxies we can observe today, faint smudges of light on our most sensitive detectors, whose light has been traveling toward us for most of the history of the universe. But because space is expanding and the expansion is accelerating, we see these galaxies as they appeared long ago. We will never see them as they are now or learn what happened to them in the intervening billions of years. The light showing us their current state will never reach us because space is expanding too fast. In the far future, the accelerating expansion will cause distant galaxies to fade from view. Galaxies beyond our local group, the cluster of galaxies bound together by gravity, will become increasingly redshifted until they disappear altogether. In perhaps 100 billion years, an astronomer in a galaxy like ours will look out and see almost nothing beyond their local group. The cosmic microwave background radiation will be redshifted so much that it becomes undetectable. Without the evidence we have today, those future astronomers might have no way to know the universe is expanding or that there was a Big Bang. The evidence will have literally expanded beyond their reach. This thought highlights how fortunate we are to be living at a time when we can observe the cosmos and uncover its history. But it also returns us to our question about what the universe expands into. The accelerating expansion creates a kind of cosmic isolation. Distant regions of space are moving away from us so fast that we're becoming causally disconnected from them. We can never send a signal to them or receive a signal from them. In a very real sense, they're moving outside our universe, defined as the region of space we can causally interact with. But those regions aren't moving into some external space. They're just moving beyond our cosmic horizon. Due to the expansion of space, they continue to exist as part of the whole universe, even though we can never observe or interact with them. This illustrates once again that the universe doesn't need an outside to expand into. Regions can become mutually inaccessible simply through the expansion of the space between them. There's another subtle point worth considering. The observable universe is expanding in a different sense than the whole universe. As time passes, light from more distant regions has time to reach us. So, the observable universe grows. The cosmic horizon moves farther away. We can see more of the whole universe as time goes on. But this growth of the observable universe is just a horizon effect, not a physical expansion. The whole universe, meanwhile, is physically expanding everywhere. Some people find it helpful to think of the observable universe as a spotlight beam that's widening over time, illuminating more and more of a dark room. The room itself, representing the whole universe, is getting bigger as space expands. But additionally, the region of the room we can see is growing as light from farther away reaches us. These are two separate effects, and it's important not to confuse them. All of this brings us to a crucial realization. When we ask what the universe is expanding into, we need to be clear about what we mean by universe. If we mean the observable universe, the answer is that it's expanding into regions of the whole universe that we couldn't previously observe. But this is just a horizon effect. If we mean the whole universe, the totality of all that exists, then the answer remains, it's not expanding into anything. It's simply growing. Space is stretching, distances are increasing, the cosmic fabric is evolving. The distinction between the observable and whole universe also helps us understand why the universe can be infinite yet still expanding. Some people struggle with the idea that something infinite can get bigger, but the observable universe is finite, and it's definitely getting larger as space expands and more distant regions come into view. The whole universe, if infinite, is expanding in the sense that the distance between any two galaxies averaged over large scales is increasing over time. The infinity doesn't get bigger because infinity isn't a number that can be increased. But the scale factor of space, the average separation between galaxies, does increase. This might still seem paradoxical, but consider this analogy. Imagine an infinite hotel with infinitely many rooms, all occupied. The manager decides to renovate, increasing the size of each room. After renovation, the hotel still has infinitely many rooms, and they're all still occupied, but each room is now larger. The hotel has expanded, even though it was already infinite. Similarly, an infinite universe can expand by increasing the distances between galaxies, even though it remains infinite in extent. The key is to remember that expansion doesn't mean adding more space at the edges, because there are no edges. Expansion means that the metric, the way we measure distances, is changing everywhere. Every region of space participates in this expansion. The observable universe, the whole universe, the regions we can see, and the regions forever beyond our reach, all are part of this same cosmic stretching, and none of it requires an outside to expand into. Alternative models and theories. While mainstream cosmology, based on the Big Bang model and general relativity, provides our best current understanding of the universe's expansion, there are alternative frameworks and theoretical extensions that add fascinating layers to our question about what the universe expands into. These ideas, while speculative and not all equally supported by evidence, open up remarkable possibilities about the nature of reality itself. One of the most intriguing concepts is the multiverse, the idea that our universe might not be the only one. The multiverse concept comes in several varieties, each with different implications for our understanding of cosmic expansion. The simplest version emerges from the theory of eternal inflation. Inflation is a period of extraordinarily rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. During inflation, which lasted perhaps from 10 to the negative 36th seconds to 10 to the negative 36th after the Big Bang, space expanded exponentially, doubling in size every minuscule instant. This inflation smoothed out irregularities in space and explains why the observable universe appears so uniform on large scales. But, according to eternal inflation theory, proposed by physicists like Alan Guth, Andre Linde, and Alexander Villington, inflation doesn't end everywhere at once. While inflation stops in some regions, allowing them to settle into the normal, slower expansion we observe today, other regions continue inflating. And within those still inflating regions, some smaller regions stop inflating, while others continue. This process goes on eternally, creating an infinite, fractal structure of bubble universes. Each bubble universe where inflation has ended becomes, in effect, a separate universe with its own properties. These bubble universes might have different physical constants, different particle physics, even different numbers of dimensions. Our observable universe would be just one bubble in this infinite froth of universes, each expanding within the eternally inflating larger space. In this model, there is something our universe expands into, the inflating space around it. Our bubble is growing, but it's growing within a larger, faster inflating medium. However, we could never access this external inflating space. The boundary of our bubble, the edge where inflation ended, is receding from us faster than light due to the rapid inflation outside. We're trapped within our bubble, unable to observe or interact with other bubbles or with the inflating space between them. This creates a nested hierarchy of expansion. The space within our bubble expands due to dark energy at a relatively sedate rate, but the inflating space outside our bubble expands vastly faster. And beyond that, there might be even larger structures we can't conceive of. The multiverse, in this view, is like an infinitely large space filled with bubbles of different sizes, each bubble being a universe like ours. Another version of the multiverse comes from quantum mechanics. The many worlds interpretation of quantum mechanics suggests that every quantum event causes the universe to split into multiple branches, with each possible outcome occurring in a different branch. In this view, there are countless parallel universes, all existing simultaneously, diverging every instant as quantum events unfold differently in each branch. This quantum multiverse doesn't involve spatial expansion in the usual sense. The different branches aren't located in different places, they're superimposed on each other, existing in a kind of quantum probability space rather than physical space. But it does suggest that our universe, meaning our particular branch of quantum reality, is just one among countless others. This raises philosophical questions about what we even mean by the universe. If reality consists of innumerable parallel branches, string theory, our most sophisticated attempt at a unified theory of physics, adds yet another layer. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings of energy. For the mathematics to work, string theory requires that space-time has 10 or 11 dimensions, far more than the 3 dimensions of space and 1 of time that we experience. In string theory, the extra dimensions are typically thought to be curled up into incredibly tiny shapes at every point in space. You could think of each point in our 3-dimensional space as actually being a tiny 6-dimensional or 7-dimensional geometric shape, far too small to detect. The particular way these extra dimensions are curled up determines the properties of particles and forces in that region of space. But here's where it gets wild. String theory allows for an enormous number of different ways the extra dimensions could be configured, perhaps 10 to the 500th power or more distinct possibilities. Each configuration would give rise to a different set of physical laws, different particle masses, different force strengths. This vast collection of possibilities is called the string landscape. Some theorists have proposed that different regions of the larger multiverse might have different configurations, different points in the string landscape. Our universe would be just one valley in this vast landscape of possibilities. Other universes might exist with entirely different physics, so different that life as we know it couldn't exist there. In some string theory models, our three-dimensional universe is a brane, a membrane-like object embedded in a higher dimensional space called the bulk. Other branes might float nearby in the bulk, potentially close in the extra dimensions, even though they're unreachable through our three dimensions. Some cosmological models have even proposed that the Big Bang might have been caused by our brane colliding with another brane in the bulk. If our universe is indeed a brane in a higher dimensional bulk, then, in a sense, our universe does expand into something, the bulk. But this bulk is so unlike normal space, governed by physics we don't understand, that it's hard to say we've answered the question in any satisfying way. And crucially, even if this is true, it doesn't change the fundamental insight. Our universe, the totality of space accessible to us, doesn't require an outside to expand into. Whether or not there's a bulk with other branes in it, our universe's expansion is intrinsic to our space-time. Another speculative idea concerns what might have existed before the Big Bang. Standard Big Bang cosmology treats the Big Bang as the beginning of time itself, which makes the question, what came before, meaningless. But some theories propose that our universe emerged from a previous phase. Perhaps it bounced back from a previous contracting phase, or perhaps it budded off from a parent universe through a process involving black holes. The cyclic universe model suggests that the universe goes through infinite cycles of expansion and contraction. After expanding for trillions of years, the universe might eventually recollapse, culminating in a big crunch. This big crunch might then bounce back into a new Big Bang, beginning another cycle. In this view, our Big Bang was just the latest in an infinite series. However, current observations make a cyclic universe problematic. The accelerating expansion driven by dark energy suggests the universe will expand forever, not recollapse. Unless something changes dramatically in the far future, there won't be a big crunch. The universe seems headed for a heat death, a state of maximum entropy where all stars have burned out, all black holes have evaporated, and everything has become a uniform, lukewarm soup of radiation and elementary particles, infinitely dilute due to eternal expansion. Some physicists have proposed that our universe might be a quantum fluctuation, a bubble of space that spontaneously appeared out of quantum vacuum. In quantum mechanics, the vacuum isn't truly empty. Virtual particles constantly pop into existence and annihilate, borrowing energy from the vacuum for brief instants allowed by the Heisenberg uncertainty principle. Perhaps the entire universe is an enormous version of this process, a quantum fluctuation that grew into all of reality. If this is true, what did the universe fluctuate out of? The answer would be some kind of quantum vacuum state, a substrate that's not space or time as we understand them, but from which space-time can emerge. This vacuum would be more fundamental than our universe, perhaps eternal and unchanging, with universes occasionally bubbling out of it like foam on an infinite ocean. All of these ideas, the multiverse from eternal inflation, the many worlds interpretation, the string landscape, branes in the bulk, cyclic universes, quantum fluctuations, remain highly speculative. Some are well-developed mathematical theories that make specific predictions. Others are more philosophical musings about what might be possible. None of them have been conclusively proven, and some may be fundamentally untestable. But they all share a common theme. They suggest that what we call the universe might be part of something larger or more complex. There might be structures or realms of existence beyond our observable universe. In some of these frameworks, our universe does expand into something, some larger space or multiverse structure. In others, the expansion remains intrinsic, even in these larger contexts. These speculative theories don't undermine the fundamental answer we've been developing. Even if our universe is a bubble in an eternally inflating multiverse, or a brain in a higher dimensional bulk, or a quantum fluctuation in some primordial vacuum, the space within our universe still expands intrinsically. The distances between galaxies increase not because they're moving into some external space, but because the fabric of space-time itself evolves. Moreover, even these larger structures, the multiverse or the bulk or the quantum vacuum, face the same question. What do they expand into or exist within? If we push the question far enough, we eventually reach a level that is truly fundamental, beyond which there's nothing more to explain. At that fundamental level, whatever it is, space or the multiverse or the vacuum or something we can't even conceive of, doesn't expand into anything. It simply is the Big Bang, beginning without a before. To fully understand cosmic expansion and the question of what the universe expands into, we need to carefully examine the Big Bang itself, the event that started everything. But the Big Bang is widely misunderstood, and many of the common misconceptions directly relate to confusion about expansion in space. The term Big Bang conjures up a specific image in most people's minds, an explosion occurring at a point in space, hurling matter outward in all directions. This picture, while vivid, is fundamentally wrong. The Big Bang was not an explosion in space. It was the beginning of space itself and of time. According to our best current theories, approximately 13.8 billion years ago, the universe began in an extraordinarily hot, dense state. All the matter and energy that exists today was compressed into a tiny volume, perhaps as small as a single point. But this point wasn't located somewhere in a pre-existing space. It was all of space at that moment. There was no outside, no surrounding emptiness into which it could explode. As time progressed from this initial state, space itself expanded, carrying matter and energy with it. The universe cooled as it expanded, like any gas cools when it expands. Energy densities decreased. Particles that had been too energetically active to combine started forming bound states. Within minutes, the first atomic nuclei formed. After about 380,000 years, atoms formed for the first time, allowing light to travel freely through space. This moment, called recombination, is what we observe today as the cosmic microwave background radiation. But what about the very beginning? What happened at the instant of the Big Bang itself? This is where our understanding becomes uncertain, because the laws of physics as we know them break down under such extreme conditions. In general relativity, when we extrapolate backward in time toward the Big Bang, we find that the universe becomes denser and hotter without limit. This suggests there was a singularity at the beginning, a point where density and temperature were infinite, and the curvature of space-time became infinite. At a singularity, general relativity's equations produce nonsensical results, like division by zero. The theory is telling us that it can't describe what happens there. Does this mean there really was a singularity? Most physicists suspect not. Instead, they interpret the singularity as a sign that general relativity is incomplete. Just as Newton's laws of motion work well for everyday objects but fail for objects moving near the speed of light, general relativity works well for describing gravity under most conditions, but fails when quantum effects become important. At the extreme energy densities near the Big Bang, quantum mechanics should become crucial for understanding gravity. But we don't yet have a complete theory of quantum gravity, a theory that successfully merges general relativity and quantum mechanics. String theory and loop quantum gravity are candidate theories, but neither is fully developed or confirmed by experiment. In some quantum gravity theories, the singularity at the Big Bang is replaced by something more complicated, but less problematic. Perhaps space and time emerge gradually from some more fundamental quantum state. Perhaps there was a previous phase of the universe that contracted down to a tiny size before bouncing back in our Big Bang. Or perhaps the concept of time itself becomes meaningless at such extreme scales, just as the concept of position becomes fuzzy in quantum mechanics. One of the deepest questions we can ask is, why is there something rather than nothing? Why does a universe exist at all? Some cosmologists have explored whether the universe could have emerged from absolutely nothing through quantum processes. The idea is that quantum mechanics allows violations of energy conservation over short timescales. Perhaps the universe is the ultimate quantum fluctuation, borrowing infinite energy for an instant and then inflating to such a large size that it can exist indefinitely. This idea faces philosophical and physical challenges. What does it mean for something to come from nothing? And what laws govern this nothing to allow universes to pop out of it? If there are laws, then the nothing isn't really nothing. It's a quantum vacuum with specific properties. We're still left asking where those laws and properties came from. Another profound question concerns time itself. We're used to thinking of time as a dimension that stretches infinitely into the past and future. But if the Big Bang was the beginning of time, then there is no before the Big Bang. Time simply starts at that moment. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question appears to make grammatical sense, but it presupposes a framework that doesn't apply. This is extraordinarily difficult to wrap our minds around. Our experience tells us that every event has a cause, and every cause happens before its effect. But if time began at the Big Bang, then the Big Bang itself had no cause in the usual sense. It was simply the first event, the beginning of causality itself. Some physicists and philosophers have proposed that time might be an emergent property, something that arises from more fundamental physics but isn't itself fundamental. In this view, asking what happened before time existed is like asking what the temperature was before temperature existed as a concept. The question assumes time is always present, but if time is emergent, there could be a more fundamental level of reality where time doesn't exist, from which our time-laden reality somehow crystallizes. The concept of the Big Bang also connects deeply to our question about what the universe expands into. If the Big Bang was the beginning of space, then there was no pre-existing space for it to occur within. The Big Bang wasn't an explosion radiating out from a center into surrounding space. It was the coming into being of space itself, happening everywhere simultaneously. Think about what this means. Every point in the universe today can trace its history back to the Big Bang. You're sitting or lying at a location that was part of the hot, dense early universe 13.8 billion years ago. The space you occupy now, the air around you, the ground beneath you, all of it was part of that primordial fireball. The Big Bang didn't happen somewhere far away. It happened right here and everywhere else, all at once. When we observe distant galaxies as they appeared billions of years ago, we're seeing them closer to the Big Bang, when the universe was younger and smaller. But those galaxies aren't located at some special place where the Big Bang occurred. They're just farther away in space, which means we see them as they were farther back in time. The Big Bang happened at their location too, just as it happened at ours. This leads to a subtle but important point. The observable universe has expanded from a very small size to its current enormous size over the past 13.8 billion years. But the whole universe, if it's infinite, was always infinite. How can something infinite come from something small? The answer is that even at the moment of the Big Bang, the whole universe was infinite, but it was infinitely dense. As space expanded, that infinite space became less dense, but it remained infinite. Alternatively, if the universe is finite but unbounded, like the surface of a sphere, then at the Big Bang, it was a very small sphere with no edges. As it expanded, it became a larger sphere, still with no edges. Either way, finite or infinite, the expansion doesn't require an outside space for the universe to grow into. The earliest moments after the Big Bang were dominated by physics we're still trying to understand. In the first tiny fraction of a second, between about 10 to the negative 36th seconds and 10 to the negative 36th seconds, the universe underwent inflation, expanding exponentially and doubling in size many times in an incomprehensibly brief interval. This inflation took a microscopic quantum fluctuation and blew it up to cosmic size, smoothing out irregularities and setting the stage for everything that came after. After inflation ended, the universe continued expanding, but at a much more sedate rate. The extreme energy of the inflation field which drove inflation decayed into ordinary matter and radiation, reheating the universe. This reheating was so intense that the universe was filled with a hot plasma of fundamental particles, quarks, gluons, electrons, neutrinos, and photons, all constantly interacting at tremendously high energies. As the universe expanded and cooled, this plasma went through a series of phase transitions, like water turning to ice as it cools. Within microseconds, quarks combine to form protons and neutrons. Within minutes, some of these protons and neutrons fused to create the nuclei of light elements, hydrogen, helium, and traces of lithium and beryllium. This process, called Big Bang nucleosynthesis, determined the primordial abundances of the light elements. And observations of these abundances today match theoretical predictions remarkably well, providing strong evidence for the Big Bang model. For the next 380,000 years, the universe was opaque to light. Photons couldn't travel far before scattering off free electrons in the plasma. But as the universe expanded and cooled, the temperature eventually dropped below about 3,000 Kelvin, cool enough for electrons to combine with nuclei to form neutral atoms. This recombination made the universe transparent for the first time. The photons that were released at that moment have been traveling through space ever since, redshifted by cosmic expansion from visible light to microwaves. This is the cosmic microwave background that we detect today, the oldest light we can observe, a baby picture of the universe at age 380,000 years. After recombination, the universe entered a period cosmologists call the cosmic dark ages. Stars hadn't formed yet, and the universe was filled with neutral hydrogen gas, dim and transparent. Gravity slowly pulled this gas into denser clumps, and within a few 100 million years, the first stars ignited. These first stars were massive and short-lived, and when they exploded as supernova, they enriched the universe with heavier elements forged in their cores. Subsequent generations of stars incorporated these elements, eventually forming planetary systems and setting the stage for complex chemistry and life. Galaxies assembled gradually over billions of years as gravity pulled matter together into larger and larger structures. The cosmic web formed as matter flowed along filaments of dark matter, Galaxy clusters formed at the densest nodes where filaments intersected. All of this occurred against the backdrop of relentless cosmic expansion, with dark energy eventually taking over as the dominant influence, accelerating the expansion rate. This history, from the Big Bang to the present, is a story of continuous change and evolution. But throughout all of it, space has been expanding not into anything external, but intrinsically. The universe has been growing from within, becoming less dense, cooling, and allowing structure to form. The Big Bang wasn't an explosion into pre-existing space. It was the beginning of space and time themselves. Understanding that time began with the Big Bang helps clarify why the question, "What is the universe expanding into?" feels so paradoxical. We're asking about a spatial beyond, but our intuition also wants a temporal before. We want to know what existed outside and before the universe. But just as there's no outside because space itself is expanding, there's no before because time itself began at the Big Bang. The universe doesn't expand into anything because there's nowhere for it to expand into. The universe doesn't come after anything because there's no time before it. Philosophical and conceptual implications. The question of what the universe expands into isn't just a scientific puzzle. It's also a deeply philosophical one. It forces us to confront the limits of human understanding and to question our most basic assumptions about reality. Let's explore some of these philosophical dimensions, examining why this question feels so urgent and what it reveals about how we think. At the heart of the matter is a fundamental tension between our intuition and the nature of reality. Evolution shaped our minds to navigate the African savanna, to understand objects moving through space, to predict where a thrown rock will land or where a fleeing animal will run. These survival skills required an intuitive grasp of space as a container, an arena in which things happen. This intuition serves us well in daily life, but it breaks down when we try to apply it to the universe as a whole. Our brains are pattern-matching machines. We take our experiences with objects in space and we generalize, assuming that the same rules apply to space itself. We've seen countless things expand into surrounding space: balloons, cities, ripples in water. We've never experienced space itself expanding intrinsically. So when we're told that space expands without expanding into anything, it sounds like nonsense. It violates our deeply ingrained mental models. This is an example of a broader phenomenon that philosophers call the limits of human cognition. There may be aspects of reality that we cannot fully understand, not because we lack sufficient intelligence or knowledge, but because our minds are structured in ways that make certain concepts fundamentally difficult or impossible to grasp. Just as a dog cannot understand calculus, not because it lacks the right training, but because its brain isn't wired for abstract mathematical thinking, we might lack the cognitive architecture to fully comprehend certain aspects of cosmology or quantum mechanics. But here's what's remarkable. Even though we can't intuitively grasp cosmic expansion, we can understand it mathematically. The equations of general relativity describe precisely how space-time curves and evolves. We can solve these equations, make predictions, and test those predictions through observations. The mathematics works, even when our intuition fails. This suggests that mathematics is giving us access to truths about reality that transcend our evolved mental limitations. This raises fascinating questions about the relationship between mathematics and physical reality. Is mathematics just a useful tool we've invented for describing nature, or is it somehow more fundamental? Does the universe literally operate according to mathematical principles, or is math just our best way of modeling what we observe? The physicist Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in describing the physical world. Why should abstract mathematical structures correspond so precisely to physical reality? Some philosophers and physicists, including Max Tegmark, have proposed that physical reality might actually be mathematical at its deepest level, that the universe is mathematics rather than merely being described by it. In this view, asking what the universe expands into is like asking what numbers exist in. Numbers don't need a container to exist in. They simply exist as abstract entities. If the universe is fundamentally mathematical, perhaps it similarly doesn't need an external container. Another philosophical dimension concerns the nature of existence itself. What does it mean for something to exist? Our everyday notion of existence ties it to location in space and time. Something exists if it's somewhere at some time. But what about space and time themselves? Do they exist? If so, how? They're not objects located somewhere. They're the framework within which location makes sense. Philosophers have long grappled with the question of whether space and time are substances in their own right or merely relations between objects. Isaac Newton believed space was absolute, a fixed background that exists independently of any matter it contains. Gottfried Leibniz argued that space is relational, that it consists only of the spatial relationships between objects and has no independent existence. General relativity seems to vindicate a version of Newton's substantivalist view. Space-time has properties independent of the matter within it. It can curve and wave even in regions devoid of matter. Gravitational waves, ripples in space-time itself, can propagate through empty space. This suggests space-time is a real thing and not just a set of relations, but quantum mechanics and some approaches to quantum gravity lean toward a relational view. In these frameworks, space-time might be an emergent phenomenon arising from more fundamental quantum relations. Just as temperature emerges from the average motion of molecules, space-time might emerge from underlying quantum entanglement between more fundamental entities. If space is emergent, then asking what it expands into becomes even more subtle. At the fundamental level, there might be no space at all, just some quantum state undergoing evolution according to quantum laws. The expansion we observe might be a property of how macroscopic space emerges from this quantum substrate, not a property of any fundamental entity. This connects to another deep question. Are there other forms of existence that we can't observe? We've discussed how regions beyond our cosmic horizon exist but can never be observed by us. Are they less real than the regions we can see? Most physicists would say no. They're just as real, we just can't access them. But this raises the question of how we define reality. If something has no observable consequences for us, no way of affecting our experiments or observations, in what sense does it exist for us? This question becomes even more pressing when we consider speculative theories like the multiverse. If there are other universes that we can never observe or interact with, are they real? The question has both scientific and philosophical dimensions. Scientifically, we might ask whether there's any way, even in principle, to test multiverse theories. Philosophically, we might ask whether science can meaningfully address questions about realms beyond all possible observation. Some philosophers argue that we should adopt what's called the principle of plenitude. If something is possible and not forbidden by any law of nature, then it exists somewhere in the multiverse or in some branch of reality. This principle seems to follow from certain formulations of quantum mechanics and inflation theory. But it leads to strange conclusions, like the existence of infinitely many copies of you, living out every possible variation of your life. The question of what the universe expands into also touches on the concept of infinity. If the universe is spatially infinite, it contains an infinite amount of matter and energy. Infinity is a concept that our finite minds struggle with. We can work with it mathematically, but do we really understand it? When we say the universe is infinite, are we making a statement about reality? Or are we just saying that our mathematical models use infinity as a convenient abstraction? There are different sizes of infinity, as mathematician Georg Cantor proved in the 19th century. The set of integers is infinite, but it's a smaller infinity than the set of real numbers. Are there different sizes of physical infinity? Could one universe be infinitely larger than another? These questions push at the boundaries of both physics and philosophy. Another profound implication concerns determinism and free will. In an infinite universe with a uniform distribution of matter, every possible configuration of atoms that doesn't violate the laws of physics will occur infinitely many times. This means there are infinitely many copies of you making every possible choice. Does this mean free will is an illusion? Or does it simply mean that your choices are real, but repeated elsewhere in the vastness of infinity? The expansion of the universe also has implications for meaning and purpose. In the far future, as the universe expands and accelerates, stars will burn out, black holes will evaporate, and everything will become a cold, dark, infinitely dilute void. This heat death seems to suggest that nothing we do ultimately matters, that all of human civilization and achievement will be erased without a trace. But does this distant fate really render everything meaningless? Many philosophers argue that meaning comes from our relationships, our experiences, our choices in the present, not from eternal permanence. The fact that the universe will end in heat death doesn't make your life or your choices any less significant now. Meaning is something we create, not something the universe owes us. The question of what the universe expands into ultimately reveals something profound about the human condition. We are finite beings trying to comprehend the infinite, creatures bound by time and space, attempting to understand the nature of time and space themselves. We evolved to understand medium-sized objects moving at medium speeds, yet we aspire to understand the smallest quantum scales and the largest cosmic scales. This aspiration is one of the most beautiful things about humanity. We're not content with just surviving. We want to understand. We look at the night sky and ask not just, what are those lights, but how did they come to be? What are they made of? How do they move? What will become of them? We push at the boundaries of knowledge, using mathematics and reason to extend our understanding far beyond what our senses can directly perceive. The fact that we can ask, what does the universe expand into, and develop a rigorous answer, even though that answer contradicts our intuition, is a testament to the power of human reasoning. We can use mathematics to access truths about reality that transcend our evolutionary limitations. We can understand that space expands intrinsically, even if we can't visualize it. We can grasp that time began at the Big Bang, even if we can't imagine a beginning of time. At the same time, we must remain humble. There are almost certainly aspects of reality we don't yet understand and perhaps cannot understand with our current theories and concepts. The singularity at the Big Bang suggests physics we don't yet know. Quantum mechanics and general relativity, our two most successful theories, are incompatible at the deepest level, suggesting both need to be superseded by something more fundamental, the nature of dark matter and dark energy, which together constitute 95% of the universe's mass energy, remains mysterious. Future generations might look back on our current understanding the way we look back on ancient cosmologies, as noble attempts to understand reality with the tools available, but ultimately limited and incomplete. Or perhaps we're closer to final answers than we think. We might be on the verge of a theory of quantum gravity that will reveal the true nature of space-time and resolve the paradoxes that currently puzzle us. Either way, the question, what does the universe expand into, will remain a beautiful example of how science progresses. It starts with a simple, intuitive question. It leads to deeper investigation and the realization that our intuitions might be wrong. It forces us to develop new conceptual frameworks and mathematical tools, and it ultimately reveals something profound about the nature of reality, even if that revelation is difficult to internalize at an intuitive level. Current research and future questions. While we've developed a robust framework for understanding cosmic expansion, many questions remain open, and active research continues to probe the nature of the universe and its evolution. Let's explore some of the current frontiers in cosmology and what future observations might reveal. One of the most pressing mysteries in modern cosmology concerns the Hubble tension. When astronomers measure the current expansion rate of the universe using nearby cosmic distance indicators like Cepheid variable stars and supernovae, they get a value of about 73 kilometers per second per megaparsec. But when they calculate what the expansion rate should be, based on observations of the cosmic microwave background radiation and the standard cosmological model, they get a lower value of about 67 kilometers per second per megaparsec. This 6 kilometer per second per megaparsec discrepancy might not sound like much, but it's statistically significant and has persisted despite increasingly precise measurements. If the discrepancy is real and not due to some systematic error in the measurements, it suggests that our standard model of cosmology is incomplete. There might be some unknown physics affecting the universe's expansion rate, perhaps related to dark energy behaving differently than we thought, or perhaps involving entirely new phenomena. Several groups are working to resolve the Hubble tension. Some focus on improving measurement techniques to make sure the discrepancy isn't an artifact of how we're measuring distances or the expansion rate. Others are exploring theoretical modifications to the standard model that might reconcile the different measurements. This active debate illustrates how even our best established cosmological frameworks remain subject to testing and refinement. Dark energy itself remains one of the deepest mysteries in physics. We know that some form of energy with negative pressure is causing the universe's expansion to accelerate, and observations suggest this dark energy constitutes about 68% of the universe's total energy density, but we don't know what it actually is. The simplest explanation is that dark energy is the cosmological constant, the same term Einstein added to his equations to create a static universe. In modern cosmology, the cosmological constant represents the energy of empty space itself, a fixed energy density that doesn't change as the universe expands. This vacuum energy has exactly the properties needed to drive accelerating expansion. But there's a profound problem with this explanation. When physicists try to calculate what the vacuum energy density should be, based on quantum field theory, they get an answer that's about 10 to the 120th power times larger than what we observe. This is the worst prediction in the history of physics, off by more than 100 orders of magnitude. Something is clearly wrong with our understanding, either in how we calculate vacuum energy or in how it relates to the cosmological constant. Alternative theories propose that dark energy might not be constant, but could change over time. Perhaps it's a new field, sometimes called quintessence, that slowly evolves as the universe expands. Different models make different predictions about how dark energy behaves, and future observations might distinguish between them. If dark energy is getting stronger over time, the universe's fate will be very different than if it remains constant. Some extreme scenarios even propose that dark energy could become so strong that it tears apart galaxies, stars, planets, atoms, and eventually even space-time itself, in an event called the Big Rip. Dark matter is equally mysterious. We know from observations of galaxy rotation curves, gravitational lensing, galaxy cluster dynamics, and the cosmic microwave background that about 80 to 5% of the matter in the universe doesn't interact with light. This dark matter must exist to explain these observations, and it played a crucial role in allowing galaxies and large-scale structure to form. But we don't know what particles make up dark matter. The leading candidates are weakly interacting massive particles, or WIMPs, hypothetical particles that interact only through gravity, and possibly the weak nuclear force. Despite decades of searching, including sophisticated detectors buried deep underground to shield them from cosmic rays, we haven't yet detected WIMPs directly. This has led some physicists to explore alternative dark matter candidates, like axions, sterile neutrinos, or even primordial black holes. Understanding dark matter and dark energy is crucial for predicting the universe's ultimate fate. Will the universe expand forever, becoming ever colder and more dilute? Will dark energy somehow change its behavior? Could there be scenarios we haven't even imagined? These questions drive ongoing research across multiple fronts. The James Webb Space Telescope, which began operations in 2022, has already transformed our view of the early universe. Looking back to when the universe was less than 1 billion years old, Webb has observed surprisingly bright and massive galaxies that formed earlier than cosmological models predicted. Some scientists speculate that early dark energy, a variant of dark energy that was present only in the first moments after the Big Bang, might explain these observations. Early dark energy would have accelerated expansion in the first few 100 million years, allowing structures to form faster than in the standard model. Webb has also detected supernovae from the cosmic dawn, observed at unprecedented distances. In late 2025, astronomers using Webb confirmed a supernova from when the universe was only 730 million years old. These observations help us trace the history of stellar evolution and cosmic enrichment with heavier elements, processes intimately connected to the universe's expansion and evolution. The telescope's observations of exoplanets, distant galaxies, and nebulae continue to reveal unexpected phenomena. From potential moon-forming disks around giant planets to unusual planetary atmospheres, Webb is showing us that the universe is more varied and complex than we realized. Each discovery adds to our understanding of how cosmic structures form and evolve within the expanding universe. On the theoretical front, physicists continue exploring modifications to general relativity that might explain dark energy without requiring a cosmological constant. Some theories propose that gravity behaves differently on very large scales, weakening in a way that mimics the effects we attribute to dark energy. Testing these theories requires precise measurements of how galaxies cluster and how the expansion rate changes over cosmic time. Other research focuses on the nature of space-time itself. Loop quantum gravity. One approach to quantum gravity suggests that space is not infinitely divisible but has a discrete structure at the smallest scales, like pixels on a screen. In this view, the fabric of space consists of tiny loops connected in a vast network. The expansion of the universe would correspond to changes in how these loops connect and relate to each other. This framework might eliminate the singularity at the Big Bang, replacing it with a quantum bounce from a previous contracting phase. String theory's landscape problem, the vast number of possible vacuum states, has led some theorists to embrace the multiverse as inevitable. If string theory is correct, and there are 10 to the 500th power or more possible vacuum configurations, and if eternal inflation produces infinitely many bubble universes, then anthropic reasoning becomes relevant. We find ourselves in a universe with the particular laws and constants we observe, because only universes with these properties can support life capable of making observations. This anthropic principle is controversial. Some scientists argue it's a legitimate way to explain otherwise inexplicable features of our universe, like why the cosmological constant has the specific value it does. Others contend it's unscientific, giving up on finding deeper explanations and settling for the observation that things must be this way or we wouldn't be here to ask about it. Meanwhile, observational cosmology continues to advance. The Dark Energy Spectroscopic Instrument, or DESI, mounted on a telescope in Arizona, is mapping millions of galaxies to trace the large-scale structure of the universe across billions of years of cosmic history. Recent results from DESI suggest hints that dark energy might be evolving over time rather than remaining constant, though these results are preliminary and require confirmation. If confirmed, this would revolutionize cosmology, suggesting dark energy is a dynamic field rather than a cosmological constant. Gravitational wave astronomy, still in its infancy following the first detection of gravitational waves in 2015, offers another window into cosmic expansion. The next generation of gravitational wave detectors, including space-based observatories like LISA, the Laser Interferometer Space Antenna planned for the 2030s, will detect waves from supermassive black hole mergers across cosmic time. These observations could provide independent measurements of the universe's expansion history, helping resolve tensions like the Hubble constant discrepancy. Quantum technology is also entering the dark matter hunt. Scientists in China and elsewhere are using quantum sensors to search for axions, hypothetical particles that are a leading dark matter candidate. These sensors use quantum spin and quantum entanglement to detect the minuscule interactions that axions might have with normal matter. Early results have dramatically improved sensitivity, pushing the search into new parameter space. All of this research circles back to our central question about what the universe expands into. As we learn more about dark energy and dark matter, about the earliest moments of cosmic history, about the geometry and ultimate fate of the universe, we're filling in details of the cosmic story. But the fundamental answer remains. The universe doesn't expand into anything. It expands intrinsically. The future will likely bring surprises. Every major advance in astronomical instrumentation has revealed phenomena we didn't anticipate. Radio astronomy revealed quasars and pulsars. Infrared astronomy unveiled galaxies hidden behind dust. Gravitational wave astronomy opened up an entirely new way of observing the cosmos. What will we find with future telescopes, future detectors, future theoretical frameworks? Perhaps we'll discover that our universe does exist within some larger structure, a multiverse or higher dimensional space. Perhaps quantum gravity will reveal that space-time emerges from something more fundamental, and expansion is just an emergent phenomenon with no deeper explanation needed. Perhaps we'll find that our questions themselves need to be reformulated in light of new physics we can't yet imagine. What seems certain is that the question of cosmic expansion will continue to inspire research and speculation. It touches on the deepest aspects of reality, the nature of space and time, the origin of everything, the ultimate fate of the cosmos. And while the technical answer that the universe expands intrinsically without expanding into anything may never feel fully satisfying to our intuitions, it represents genuine progress in understanding the cosmos. Conclusion. As we drift toward the end of our cosmic journey, let's take a moment to reflect on what we've discovered about this beautiful paradox at the heart of cosmology. We began with a simple question. If the universe is expanding, what is it expanding into? This question feels so natural, so obvious, that it seems like it must have an answer. Yet we've learned that the question itself rests on an assumption. The assumption that expansion must be expansion into something, that space must exist within a larger container. The universe, we've discovered, is not an object in space. It is space, or more precisely, it is space-time, the four-dimensional fabric in which events occur and objects exist. When cosmologists say the universe is expanding, they mean that this fabric is stretching, that distances between distant objects are increasing, that the metric of space is evolving over time. This expansion doesn't require an outside to expand into, because outside is a spatial concept that only makes sense within the universe. Asking what's outside the universe is like asking what's north of the North Pole. The question uses words and concepts in ways that don't apply to the situation. We've seen how this counterintuitive truth emerges from Einstein's general relativity, which revealed that space and time are not fixed backgrounds, but dynamic participants in physical processes. Space can curve, warp, stretch, and shrink. The expansion of the universe is simply one manifestation of this flexibility. We've explored how the universe could be finite yet unbounded, having a definite volume but no edge, like the two-dimensional surface of a sphere extended to 3 dimensions. Or it could be infinite, stretching on forever in all directions, with the expansion meaning that the density decreases over time as the same amount of matter fills an ever larger infinite space. We've distinguished between the observable universe, the finite region from which light has had time to reach us, and the whole universe, which might be vastly larger or even infinite. The expansion affects both, but in different ways. The observable universe grows as light from farther away reaches us, while the whole universe expands intrinsically, with space stretching everywhere. We've considered speculative ideas like the multiverse, where our universe might be one bubble among infinitely many in an eternally inflating larger space. Even if true, this doesn't change the fundamental insight. Our universe still expands intrinsically, and the larger multiverse structure would face the same question. What does it expand into? Push the question far enough, and you reach something fundamental that simply is, without existing within anything else. We've thought about the Big Bang, not as an explosion occurring at a point, but as the beginning of space and time themselves. Every location in the universe was part of the hot, dense, early cosmos. The Big Bang happened everywhere at once, or more precisely, it was the first moment of everywhere. We've grappled with the profound difficulty of understanding these concepts intuitively. Our minds evolved to navigate a world of medium-sized objects moving at medium speeds, not to comprehend the nature of space and time themselves. We can understand cosmic expansion mathematically and reason about it logically, but it may never feel natural to us the way understanding a thrown ball's trajectory feels natural. Yet there's something beautiful in this struggle. It shows us both the limits and the extraordinary capabilities of human reasoning. We're limited by our evolutionary history and our cognitive architecture, yet we've managed to extend our understanding far beyond our everyday experience. Using mathematics as a language and experiments as a guide, we've uncovered truths about reality that our ancestors couldn't have imagined and that our intuitions still can't fully grasp. The expansion of the universe is one of the most well-established facts in cosmology. Every observation confirms it. The redshift of distant galaxies, the cooling of the cosmic microwave background radiation, the abundances of light elements, the large-scale structure of galaxy distributions all point to a universe that was hotter and denser in the past and has been expanding for nearly 14 billion years. Yet, mysteries remain. We don't know what dark matter is. We don't know what dark energy is. We don't have a complete theory of quantum gravity to tell us what happened at the Big Bang's first instant. We don't know whether the universe is finite or infinite. We don't know if there are other universes. We don't know the universe's ultimate fate. These open questions are part of what makes cosmology so exciting. We're living in a golden age of observational cosmology, with powerful telescopes revealing the distant universe in unprecedented detail, and theoretical cosmology, where ideas once considered pure speculation are becoming testable. The coming decades will likely bring answers to some of these mysteries, and undoubtedly new mysteries we haven't yet imagined. As you lie here, breathing slowly, feeling the comfort of your resting place, you might find it remarkable that humans have learned these things about the cosmos. Generations of astronomers peering through telescopes, physicists working through equations, and countless people building instruments and analyzing data have combined their efforts to reveal the universe's nature. And what they found is a cosmos grander and stranger than anything imagined in ancient cosmologies. A universe 13.8 billion years old, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. A universe governed by mathematical laws we can discover and understand. A universe that had a beginning and will have an end, or will expand forever into cold darkness. A universe whose expansion creates the very question we've been exploring tonight. The universe expands without expanding into anything, because it is all there is. Space is not a container, but the relationship between things. Time is not a river flowing through eternity, but the dimension of change. Together, space-time is the fabric of reality, and its expansion is simply how that fabric evolves. Understanding this doesn't diminish the wonder. If anything, it deepens it. The universe is not just large, it's structured in ways that challenge our most basic assumptions. It's not just old, it's dynamic, changing, evolving. From a beginning we can trace back nearly 14 billion years. It's not just full of matter and energy, it's dominated by mysterious dark components we're only beginning to understand. As you drift off to sleep, perhaps you'll dream of cosmic expanses, of space stretching and galaxies receding, of light traveling for billions of years across the void. Perhaps you'll dream of the Big Bang, of everything emerging from a hot, dense state, of the first atoms forming, of the first stars igniting, of galaxies assembling into the cosmic web. Or perhaps you'll simply rest, knowing that you've touched something profound tonight. You've encountered a deep truth about the nature of reality. The universe doesn't need an outside because it is the totality of existence. It expands intrinsically, growing from within, creating more space between the galaxies, cooling and evolving as it goes. This is the cosmos we inhabit. Strange and wonderful, comprehensible through science, yet ultimately mysterious. It's a universe that can be studied and understood, yet never fully grasped by our limited minds. It's a reality that rewards curiosity and inquiry, revealing layer after layer of structure and meaning. So rest now. Let your thoughts drift like galaxies moving apart in the cosmic expansion. Feel yourself floating in the vastness of space and time, a tiny conscious being in an immense universe, yet connected to it all through the same fundamental forces and particles. You are made of stardust, atoms forged in ancient stars and scattered across space when those stars exploded. You are part of this expanding cosmos, a way for the universe to know itself. Sleep well, cosmic traveler. Dream of infinite space that needs no outside, of time that had a beginning, of a universe that simply is. And know that tomorrow, the cosmos will still be here, still expanding, still full of mysteries waiting to be explored. Until next time, may your dreams be as vast as the universe itself.